Welcome back to Chapter 1.4, The Law of Large Numbers and the Central Limit Theorem, Part 2 of 10. In Part 1, we stated the law of large numbers. The sample mean converges in probability to the true mean. Now we prove it almost for free using one beautifully crude tool you can carry for the rest of your life, Chebyshev's inequality. Here is the tool, Chebyshev's inequality. For any random variable, y with mean mu sub y and variance sigma sub y squared, and any positive epsilon, the probability that y strays at least epsilon from its mean is at most sigma sub y squared, divided by epsilon squared. The idea in a sentence, variance, is the average squared distance from the mean, so if a lot of probability sat far out at distance epsilon or more, the variance would have to be large. Turn that around, and small variance forbids much probability from sitting far out. Chebyshev makes no assumption about the shape of the distribution, only that it has a finite variance, so it is deliberately crude and almost always loose. But loose is exactly what we want, because we are not trying to nail down a probability. We are trying to prove one vanishes, and a crude upper bound that goes to 0 settles that just as decisively as a sharp one would. Now apply Chebyshev to the sample mean. We already know, this was last chapter's punchline, that the sample mean has mean mu and variance sigma squared over n. Plug that in. The probability that the sample mean misses mu by at least epsilon is at most sigma squared divided by n times epsilon squared. Stare at the right-hand side. Epsilon is whatever you fixed, sigma squared is a fixed property of the population, but n sits in the denominator. As n goes to infinity, that bound goes to 0. The probability of missing mu by more than epsilon is squeezed to nothing. That is the weak law, and we got it almost for free, because the real work, establishing that the variance of the sample mean equals sigma squared over n, was done last chapter. Notice what the engine of the law is. Averaging cancels noise. Each draw has its own variance, sigma squared, but when you average n independent draws, the wiggles partly cancel, and the variance of the average falls like 1 over n. Independence is what makes the cancellation work. Deviations from mu are as likely to offset as to reinforce, so the sum of n deviations grows only like the square root of n rather than like n, and dividing by n leaves something that shrinks. If the draws were instead strongly correlated, every observation echoing the last, as in a trending time series, the deviations would reinforce instead of cancel, the rate would degrade, and the law would arrive slowly or not at all. That foreshadows why time series data demand special standard errors in week 2. And the square root of n attached to standard errors is this same fact. The standard deviation of the sample mean is sigma over the square root of n, so to have your uncertainty, you must quadruple your sample. To summarize Part 2, Chebyshev's inequality fed the fact that the sample mean has variance. Sigma squared over n forces the probability of a meaningful miss to 0 as n grows. That is the weak law, proved almost for free. The engine underneath is that averaging cancels noise, and independence is what lets the deviations offset rather than reinforce. Remember too that the square root of n law means having your uncertainty cost you a quadrupling of your sample. In Part 3, we stop proving and start watching. We follow a single running average as it grows and see the law of large numbers happen in pixels.